Yeah.
All right, whenever you're ready, man.
Okay, so I'm Amir, and I want to talk about using graph partitioning methods to enhance the greedy FPGA packing algorithms. Okay. Oh, sorry. So, we'll go through two papers. One by Chen et al. Called Improving Timing-Driven FPGA Packing with Physical Information, and another one by I'm not sure if I'm pronouncing the name correctly by Vercruise et al. Called How Preserving Circuit Design Hierarchy During FPGA Packing Leads to Better Performance. Unfortunately, I think the next paper will go for next week or some other time. So we won't go through it today, but I'd like to go through it sometime. And also some talk about how relevant these approaches are in current times because so the first paper is from 2007 um, and is mostly talking about FPGAs that are very homogeneous. So uh, no block RAMs, no DSP, nothing. It's just CLBs in there. And the second one uses is based upon VTR version 7, which is I think around a decade old at this point. So, a little brief background on FPGA packing. Um, as I said, this paper is from 2007, so FPGAs are pretty simple. You have a bunch of CLBs connected to each other by a reconfigurable routing network. And so inside each CLB, you have a hierarchy of things that go deep down until you reach basically lookup tables and registers. And FPGA packing, basically, you need to take these lookup tables and registers and put them in this hierarchy. You need to kind of build this hierarchy. So to speak in VPR terms, basically, this hierarchy that is showing on the screen right now is basically encoded in VPR by this data structure called the TPB type. And you basically have a tree that goes down. Okay, you have a CLB, and inside a CLB, you have these mid-level hierarchy slice, a logic cell, and then until you reach a lookup table or register with another, like a primitive or an atom, basically. And in packing, you need to build another tree that's the equivalent of this tree, but with actual atoms in the netlist. So you have maybe a lookup table in the netlist and a register in the netlist, and you have to basically make up this hierarchy with the atoms you have in the netlist, or I guess to be more accurate, with the molecules you have in the netlist.
Just to interrupt you briefly,
Yeah,
what's the objective for packing? So is it just finding a feasible solution? So I have 800
right,
LUTs, I have 800 site locations, just put them randomly and they fit? Or is
right.
there a better way?
Thank you for asking this. I actually forgot to talk about this. So the goal for packing is so first thing you need to do this for FPGAs because well you have to. You have CLBs and everything. And the other one that you should do this is because you're making the complexity of the following parts much lower. So you will start with a netlist consists of like maybe a million atoms, and then you pack them together and you go down an order of magnitude, basically. So you're making the following stages, the placement and routing stage is much easier, first and foremost. And also the goal here would be to have um, a packing that's trying to minimize the connections that go outside of these CLBs. So the routing resources that are connecting CLBs to each other are slow and rare, and you don't want to and you want to contain as much of the connections inside these CLBs as possible. This gets you a low wire length number, this gets you a low the critical path delay and everything like that. So a good packing would do this for you, and you also need to do packing anyway.
So I just want to just check something. So I don't think you need to necessarily do packing. There are algorithms that can do flat placement, for example, and flat routing. which will be able to, for example, do simulated annealing on the LUTs and then do simulated annealing on the flip-flops at that level, and then do routing at a flat level. That does exist, but in VTR, we don't necessarily do that
Yeah.
because we want to try and shrink, as you said, shrink the problem. And also, when we are early on and we're doing packing, we want to bring wires into the clusters so that it makes the problem easier. And hopefully, after placement, we chose good clusters so that the routed wire length and creep CPD is good. I think that makes sense.
Yeah, exactly. So, we start with DPAC, which is the first packing algorithm in the paper that we're discussing. So the main idea here is to do recursive bipartitioning with hMetis to do a rough global placement. So hMetis does a minimum cut partitioning. What it does is it takes a netlist, a hypergraph, and it cuts it into multiple partitions. And the goal is to have the minimum number of connections going between partitions. So, Deepak uses hMetis to cut the netlist into two separate partitions, and then it does that again and again to do a rough global placement and use that global placement to guide packing. So here in this diagram, we have a netlist before the partitioning, and then we do a cut, a vertical cut here. So everything on the left is part of one partition, everything on the right is part of another partition, and so we have a cut line here that's cutting three connections. And then this is recursive, so we do that again to each partition. So here the left partition is cut into two partitions, and then we do it on, so here we do it horizontally, and then the next partition goes vertically. One thing to keep in mind here is that these square boxes don't exactly have a position here. The reason they're spread out is because it makes the figure cleaner. So you can think of the all of these to have the position of being at the exact center. And now that we do one cut, all of these ones on the left are at the exact center of this partition. So let me draw here. So everything would be here, and then everything would be here. Then here you have all of them would be here, and all of them would be here. So you keep doing that, and you essentially get a grid. And in that grid, so if you get the grid fine enough, you have a pretty good placement. So you have a bunch of atoms here and you have a bunch of atoms here, and you get an idea of where things should be, which is not very sophisticated, but it's kind of it is kind of a global placement at the end.
Oh, it certainly is. And it looks like
Yeah.
it's very similar to analytical placement, but it looks like they only have connectivity terms. It's not like they're trying to minimize wire length. They're really just trying to minimize the amount of wires leaving clusters. That's really interesting.
Yeah, this is basically just the normal hMetis flow, essentially. They don't do anything special with their partitioning. So, how do I clean this stuff up? Sorry.
There's like a button on the left side that's where you start drawing. On the bottom is a little trash can.
Ah, okay. Thank you. All right, so DPAC selects the critical seed, same algorithm as TVPAC, which is an old version of the packing algorithm used in VTR. Essentially, it decides like what is a very critical atom to the net list and lets us start packing that first. Because we at this stage we really have very limited information. You have a lot of ties, so you might have like 20 atoms with the exact same criticality. So they use an extra tie-breaking mechanism, which is path counting. The basic idea here would be that molecules with multiple critical paths are more critical. So here let's say you have two critical paths here, the one on top and the one on bottom. These two, excuse me, these two atoms are more critical than the other four because these are shared between like two paths, while these four are just in one critical path. So they use that as a tie-breaking mechanism. They take that seed and cluster it with the next best thing. So let's say you have this one, it's really connected to like it's connected to these three atoms, right? And so this one here, I guess, is the most critical thing it's connected to. So it clusters these two together, and then the next best thing would be this one, and it just goes on until the CLB is full. If the CLB is not full, but all the pins are used, so you would have something you have a CLB that can fit in like eight lookup tables and you used four lookup tables, but all the output and input pins of your CLB is used, it enters a hill climbing phase. So it just adds things, hoping that it gets better, right? So you might have four pins used, and then you add something to it that was so you have an atom that's actually driving two of the input pins of your CLB. You add it into the cluster. And so you're freeing those two pins basically, and you might get an improvement in that regard. So it enters a hill climbing phase, hoping that that happens. And if it doesn't happen, if the hill climbing is not successful, it just accepts the last legal clustering at the end. What are the cost functions here? So the cost here is basically this is a term, right? This is about the connectivity, and this is about the criticality. The connectivity here is the sum of the fan out. So this is like the number of edges in the net, right? And minus one, that would be basically the fan out of the net. So you have a seed I and then another thing J, right? I guess let me start from again. The cost function for the two atoms I and J would be this. This is the connectivity between the I and J, which is the sum of the fan out of the nets that have I and J in them. And this is the criticality between I and J. And this is just the criticality metric of the net, nothing special. Any question here?
Yeah, I'm just so the partitioning that happened before, so that's before this step. This step is now we've done the partitioning. Are
Yes.
we ever going to cross the partition lines when we're doing this, or are we only going to stay within our partitions?
Uh, yes, you can cross the partition lines here. They don't do any restrictions between the partitions here, so they only use it to guide the this cost function here. And you might ask, so this cost function doesn't have anything to do with distance, and that would be true. So they add a new term for
Ah.
the spatial information later. So you have those same two terms, and you have two separate factors, and then the remainder of those two factors would be times the distance between the two atoms. And as you can see, this is a minus, so if things are far apart, the cost goes down. So it's really punishing the pack carrier for like don't pack things that are far away from each other. Basically, that's the cost function that they use.
Oh wait, sorry, can you go back? Dist, is that literally the distance in tiles?
This is the distance in tiles divided by the size of the FPGA. So in yeah.
Gotcha. Okay, yeah, because I was worried because E and crit, I think, are numbers between 0 and 1, or at least really close to that.
Yeah.
So if you have dist, that would really overwhelm your cost terms. That makes
Oh
sense.
yeah, no, they normalized it to the size of the device.
Gotcha. That's actually a really important thing. That's
Yeah.
cool.
So hybridized packing. So they then talk about a different algorithm, which is kind of built onto the previous one. It's called HD pack, which is the previous algorithm plus something they call hybrid first choice clustering.
Mm.
What is that? So let's okay, let me. So what they do is they first do a pairwise packing. So let's go through the code. For each edge in the net list, then go for each cell in that net, right? So you have this is an atom basically. So for each atom in a net, go and compute the cost for basically pairing these two atoms together. What that means is essentially they go through the entire netlist and then compute. how much do these two atoms want to be together? And so they have this list, right? So they sort all the costs from largest cost to lowest, and they have this term that I'll talk about later. And then they go through this list from the highest cost, and then so you have this cost between the atoms I and atom J, and then pack them together, right? You just want to pack them together. If you can't pack them together, just go for the next one and just do that. So what you do here, um, so you packed I and J together, right? And then the next pair would be, for example, J and K, right? J is already clustered, and then you have this unclustered atom called K. You would still cluster that together. So now you have a cluster of three things,
Oh,
right? This approach does good at small, like starting clusters. They say that this approach works really well for starting clusters. But if you do the entire clustering with this approach, you would end up with a huge number of clusters. So a lot of blocks, you probably can't fit it in your device. It's going to be a disaster. So they add this stopping cost term that say that, okay, so if we have a pairing that's just not too good, right? We only want to pair things that are really want to be paired together. If we get to a point where it's just, these two are don't want to be together that bad. So, if they ever reach that point, they just stop doing this and they go with Deepak and then just run Deepak on the remaining atoms on the net list. So essentially what HDPack does, it starts a lot of clusters that are unfinished, right? And then finishes all the clusters off with the previous greedy algorithm.
that's really interesting. So this is very similar to the LSC algorithm that I don't know if we talked about this in a reading group prior, but LSC, you have the cost ij, cost jk. What LSC would have done in a similar way is it would create two hypothetical clusters, ij and jk, in space somewhere. And by the end of it, once they decide which clusters to create, one of them will be realized and the other one will be destroyed. What you're saying here, though, is a little different. You're saying if I had cost ij, cost jk, and I do one cluster, then I do the other one, it will bring it into the other one. So we'll end up with a cluster with three atoms in it. Is that correct?
Yeah, that is true.
Gotcha. So it's a bit more of a greedy approach, but it's still it's a good starting point, and I get that. That makes sense.
Yeah. So they use this as a starting point. I just had one question here, and I'm not entirely sure. Is this a stage n squared? Because they're doing pairwise everything, right?
It's on
That's
the order of the number of edges. So technically speaking, on a full clique netlist, so every cell connects to every other cell, yes, the number of edges would be quadratic with the number of blocks.
hmm.
But in real netlists, you don't find that the number of
Yeah, that's
edges is
true.
quadratic. Now, it's
Yeah.
still higher than the number of blocks, but I tend to find the number of edges to be around the number of cells on the order. So, but it's a good question because you're saying I see an I and a J, isn't that squared? It's number of edges, I believe.
Yeah. Yeah,
Or
they do a loop on the edges and then they go for the all of the everything that's connected by the edge.
oh,
Yeah.
it's everything connected by the edge. So it's I, J, and E. They call it an edge. I would call that net E. And
That's a
then,
net. Yeah, exactly.
yeah, so I think line three, I think should say net E. And then line four should not say cell IJ. It really should say edge E in net. Because then that would make it more clear. We're just going over the number of edges.
Yeah, that's
It's a
true.
good question.
Yeah. So then they do basically a study on like how good and like how high resolution does our global placement needs to be. So in here we have two uh, graphs here. So the x-axis is the partition depth. So if, for example, partition depth 4, you would cut the netlist in two partitions 4 times. So you have 2 to the power of 4, I think, or maybe 2 to the power of 5 or something. I might be off by one, but you do 2 to the power of 4 partitions here for partition depth 4. So they see that there is a very diminishing returns thing going on here. So doing four layers of bipartitioning versus doing 14 layers of bipartitioning doesn't do much of a difference here. And that goes for that would be var length, and that's for CPD, and it's basically the same thing here, which is kind of interesting. So, like going with a high resolution goal placement does not necessarily help the packing that much,
What's the
I guess.
difference in the numbers? So I see on the bottom you have partition depth 0, 2, 4. And then what's the legend saying? I see 2, 4, 8, and 12.
So this is the number of logic elements in a CLB. So this has like two lookup
Oh.
table whatever's in the CLB. This has four, and it goes like that.
Oh, interesting. Okay, I see. We tend to use, how much do we use in VTR? It's K6 N12, so we usually use N12. So I'm looking at the X's here just to see, just to put it in context for myself. Yeah, that one's right in the middle. That's interesting.
Hmm.
Huh. And yeah, you can see it kind of plateau. Do you know what device size they were working towards? You said it was a homogeneous architecture.
Um, it's somewhere in the paper, but I don't really have it in here. Yeah.
Gotcha. Because I feel like this would change the results, or at least because I think it would still plateau, but I wonder if it will move the inflection point
Hmm.
if you have a bigger and bigger device.
Yeah, that could be a possibility. So one thing I'll get into that this paper is from 2007, so there's a bit of there are some limitations here.
Hmm.
So the results, and they ran the MCNC benchmarks.
Hmm.
So runtime comparison versus baseline, they get some slowdown on like the N12 devices. So maybe like 13%, 15%. Um,
Hmm.
um, Interestingly, HD pack, which does the hybrid pairwise stuff, at first is faster than D pack, which
Hmm.
which is kind of interesting here.
That kind of makes sense,
After you,
actually.
yeah.
Hmm.
The results here. So they have their so DPAG and HDPAG, they both can work without physical information. So without any physical information, the wire length improved by 15% and 2%. With physical information, it's 21% and 94%. So I guess adding physical information, you get 8% better wire length and 4% better CPD,
Hmm.
um, which is nice.
What was their
So
baseline?
the baseline is TV pack.
Ah, gotcha.
Yeah. So that would be the VPR point version 4.3 or something like that.
Yeah, that was
So
before AA packs. That was before Jason Liu's work, I believe.
yeah, this is I think before VTR existed.
Yes, I think that was TV Pack was its own packing tool at one point, I
Yeah.
believe.
So some thoughts. There's diminishing returns on guiding the packing with high resolution spatial information. I guess I had a question that's is HDPAC O of n squared, which I guess technically it is, but in practice not really. But still something to be like wary about if you're doing modern designs. So this work was done when FPGAs were homogeneous. So the packing problem is much more complicated now. So if you notice here, so they just casually made an entirely new packing algorithm separate from TV pack. You cannot do that now. You like if you want to do a new packing algorithm from scratch, good luck. So yeah, they basically have D pack and HD pack, and then they compare it with TV pack. So and you have essentially three separate packing algorithms compared now. You can't really do that these days because the packing problem is incredibly complicated. Um, so any thoughts by the people in attendance?
So I do agree with your idea that there's no point in trying to make a new packing algorithm in VTR. So AA pack has a really complicated problem because it has to work on any given architecture. If you had a fixed architecture, for example,
Oh,
you only have 6 LUTs in a basic CLB structure, even with hard macros like RAMs and DSPs, you can still make your own packing algorithm. But in the context of VTR, trying to redo what they've been doing it would be tricky, but I don't think impossible. So actually, could you go back to the pseudocode that you showed with the cost ij, that one? What made LSC tricky to implement, which we never actually ended up doing because it was just too crazy, was because we cannot have multiple versions of the same cluster existing. That
Yeah,
was just a nightmare to get working in VTR. Here, though, a cell will only ever exist in one and only one place, either in
yeah,
a cluster, one single cluster, or out in space and nowhere. I think we can still do something like this. It would be interesting to explore. It
yeah.
would be slower than what we have because right now we have just pure greedy. And trying to do this at the beginning, I worry would be a little slow, but I'm sure there are tricks you can do to speed this up. That's super interesting.
Yeah, it's a very nice idea. I agree.
Hmm.
Yeah. So that was 2007. What about now? So the first thing to talk about it is MCNC, and here I grab a screenshot from the VTR documentation. The MCNC benchmarks are not recommended for modern FPGA CAD research. They're very small. The few registers, no hard block. It's unrepresentative of modern FPGA usage. So take the numbers with a grain of salt, obviously, but the ideas I think could still make sense. And just to like give you some context, I think the largest benchmark on the MCNC suit is like 4,000 atoms, something like
Mhm.
that. It's very small. So both of these algorithms do unrelated clustering. So after running out of related atoms that are connected to each other and like a bunch of different criteria, they just fill the cluster with unrelated atoms, and you get a dense but worse packing. HDPAC and DPAC, they mitigate this by using a cost factor
Yeah.
that favors closer atoms. So if we get back to the cost function here, um, so you essentially do it minus the distance between two atoms. So if you have two atoms that are really far away from each other, you essentially kind of don't pack them together. Like you do, but it's very heavily penalized. So
That final bullet. Mhm. Uh,
it basically keeps the unrelated atoms from being too unrelated in a sense.
If you want my opinion, I think that final bullet point is where they got that 6% or 8% wire length and 3% CPD. From my own experiments in the analytical placer, if you turn on unrelated clustering, the old one, which is just put anything on the chip anywhere inside, you just screw over your quality. It gets a lot worse. If you attenuate it with distance information by saying only cluster the unrelated ones that are nearby, you can actually save yourself a lot. Like I've actually been finding that the unrelated clustering in that will create denser clusters and the quality remains somewhat the same. So I think they actually they were doing like bloodletting. Bloodletting, when you stop doing bloodletting, people get healthier because bloodletting was actually more harmful than good. I think the unrelated clustering was actually doing more harm than good here.
Yeah,
So that's my opinion on this paper. I think that that spatial information was really just helping to create denser clusters with good quality.
yeah. I also kind of seen the same thing happening in my own experiment, so I kind of agree with you. Yeah, I agree with your take on this.
Hmm.
Okay, so VTR 8 and VTR 9 don't do that. So by default, VTR stops packing once it runs out of related atoms, unless the just doesn't fit on a device or the floor plan constraints. So VTR 8 got 20% better bar length and 3% better CPD just because of this. Probably a coincidence, but it's close to the 20% better bar length and 6% better CPD reported by HDPAC, so something to keep in mind. Um, AP does what DPAC does with regards to using a global placement to guide packing. The role of AP in the flow is not just guiding packing, but so it's not possible to say like how much benefit comes from just that. But overall, as of 2 months ago, AP got 6% better bar length on VTR, Titan, and Coast benchmarks, which is close to HDPAC, which is close to what HDPAC got when you compare the without versus with spatial information. So if we go back a couple of slides, um, I did again. Okay, so here you got like 8% better wire length and 4% better critical path delay when you added in the physical information. And so as of 2 months ago, you got the same results. AP got the same results, but obviously, like you can pinpoint all of that on AP Pack. So it seems like the overall idea of guiding packing with like the placement information is still valid, even with unrelated clustering turned off. So any questions?
I think that makes sense. I would be careful though, trying to put a modern lens on such an old paper. We are now in an age where we have heterogeneous FPGAs. They're absolutely, utterly massive, and we also know what we have now. So it does change some of the. I don't think you can also just say, "Oh, this 8% came from here," without us doing some of the experiments. But I think it's good to think about it and also see where and help it to inform future decisions.
Yeah, absolutely. So I guess that's all I have for this week. So if you have any questions or thoughts, I'll be happy to hear them.
All right. If no, there's no other questions. Thank you so much, Amir, for the talk, and
Okay,
we'll see you next
great.
week.
No
Oh, wait,
worries.
James, do you have a question?
No, just thank you, Amir. That was very detailed.
Yeah.